In the mid-1990s, the head of a university statistics department picked up the phone and made one of the strangest complaints in the history of computing. He said that his department could not send email more than 500 miles. Now, read that sentence again, because it should not be possible. Email does not have a range. It is not a walkie-talkie. There is no distance field in the protocol. And yet he was completely, measurably, reproducibly right. Mail to the next city went through. Mail across the country bounced. The bug had a radius. In this video we are going to look at 5 bug reports that sounded like nonsense and turned out to be perfectly accurate descriptions of reality. 5 cases where the machine was doing exactly what somebody told it to do, and nobody could work out who. One ground rule before we start, because this genre is full of rubbish. Every case in this video was checked against a primary or near-primary source before I wrote the script. One very famous story did not survive that check. You have probably heard about the car that would only refuse to start when its owner bought vanilla ice cream. It is a wonderful story. It is also, as far as anyone can tell, folklore. Snopes traces it back to a magazine in 1978 and nobody has ever produced the customer, the engineer, or the car. So it is not in this video. Folklore is not engineering. Let's start with the 500-mile email, because it is the most beautiful bug ever documented, and because the man who solved it wrote the whole thing up himself. His name is Trey Harris, and he was the email administrator at the University of North Carolina. The call goes roughly like this. The chairman of statistics says, "We are having trouble sending mail more than 500 miles. Harris asks him to repeat that. The chairman says it again. Email to universities in the same state was arriving. Email to the West Coast was not. And the department had actually gone to the trouble of testing it. They had a geostatistician on staff, which is exactly the person you want on this problem, and he had plotted the failures on a map. The boundary was somewhere around 520 miles. The first useful question in any investigation is, what changed? And something had. A few days earlier a consultant had patched the operating system on the mail server. That patch quietly reverted the mail software, SendMail, from version 8 back to version 5. But it left the version 8 configuration file exactly where it was. So now you have an old program reading a new configuration file, full of settings that the old program has never heard of. Here is where it becomes genuinely elegant. When the old binary hit a setting it did not recognize, it did not complain. It did not warn. It simply left that value at 0, because 0 is what uninitialized memory gives you. And one of the settings it did not recognize was the timeout for connecting to a remote mail server. Now, if you set a timeout to 0, what do you think happens? Most people's instinct is that 0 means no limit. Wait forever. It does not. 0 means do not wait. On that particular machine, under its normal load, Harris measured that a 0 timeout would abandon a connection attempt after slightly more than 3 milliseconds. And now put the last piece in. The campus network was fully switched, which means outbound packets were not sitting in queues waiting for Reuters. The time to open a connection to a lightly loaded machine somewhere else was therefore dominated by one thing only, how long light takes to get there and back. So take 3 milliseconds, multiply by the speed of light in fiber, and you get a radius of roughly 558 miles. The professor said 500. The geostatistician measured 520. The physics said 558. That is not a coincidence. That is a match. So what do you take from this one? This. When a user gives you a bug report that sounds impossible, they are almost never wrong about what they saw. They are only wrong about what it means. The chairman's description was flawless. Mail fails beyond 500 miles. It was the most accurate possible summary of a 0 millisecond timeout. He just did not have the vocabulary to say it in networking terms. Listen to the symptom. Distrust only the diagnosis. Right, first question, and I want you to actually pause the video for this one. A user tells you that your application only breaks on Fridays. Before you roll your eyes, name 2 things that could genuinely, mechanically be different on a Friday. Pause now, think about it, and put your answer in the comments. I will tell you mine after the next case, and I promise you the real-world answer is stranger than whatever you just thought of. Case 2. This one is not from a lab. This is a national election. Belgium, the 18th of May, 2003. A federal election, counted electronically. In the Brussels district of Schaerbeek, the results come in and something is badly wrong with one candidate's total. A candidate who was not remotely in contention had picked up thousands of votes out of nowhere. And here is the only reason anybody noticed. The error was not caught by an audit of that candidate. It was caught because the total votes cast in the district came out larger than the number of people registered to vote there. That is an impossible number. More votes than voters. That single arithmetic sanity check is the entire reason this story has an ending. Now look at the size of the discrepancy, because this is where an investigator's ears prick up. The candidate had not gained roughly 4,000 votes. She had gained exactly 4,096. And 4,096 is 2 multiplied by itself 12 times. It is a power of 2. That is not what fraud looks like, and it is not what a typing mistake looks like. That is the fingerprint of one single binary digit, somewhere in memory, changing from a 0 to a 1. So what flips a bit? A single event upset. A high-energy particle, ultimately traceable to cosmic radiation hitting the upper atmosphere, passes through a memory cell and dumps just enough charge to flip it. The stored value changes. No component is broken. Run a diagnostic afterwards and the memory tests perfectly, because nothing is faulty. The bit was simply, briefly, hit. Investigators ruled out fraud, ruled out a software defect, and this is the explanation that was accepted. Your immediate reaction is probably, why has this never happened to me? 2 reasons. First, it is rare per chip, but it is not rare at scale, which is why every serious server on Earth uses error-correcting memory. ECC memory carries extra bits so that a single flip bit is detected and silently repaired before your program ever sees it. Second, on your laptop, which mostly does not have ECC, it probably has happened. A flipped bit in a photo is a slightly wrong pixel. A flipped bit in a running program is one mysterious crash that you rebooted and forgot about. And the lesson here is the most practically useful thing in this entire video. That election error was not caught by a unit test, because no test suite on Earth has a test case for cosmic rays. It was caught by an invariant. A statement about the system that must be true no matter what, votes cast can never exceed registered voters. Write those into your systems. Totals that must reconcile. Balances that must never go negative. Counts that must never exceed capacity. An invariant catches the failure you did not imagine, and every other kind of test only catches the failures you did. Case 3. And this is my answer to the question I asked you earlier, about the user who says it only breaks on Fridays. 2009. A bug report is filed against Ubuntu Linux with a title that reads like a joke. Printing from the Office suite does not work on Tuesdays. Not intermittently. Not usually. On Tuesday it fails, and on every other day of the week it works, and yes, they had checked, repeatedly, for several weeks. The instinct is to blame the word processor, because that is the thing the user was touching. The word processor was innocent. So was the printer, and so was the print queue. To find the real culprit you have to know what happens to a document between clicking print and the paper moving, and there is a step in there that almost nobody thinks about. Before the system can print your document, it has to work out what the document actually is. On a Unix-like system, that job belongs to a utility called file, which does not trust the file extension. It opens the file and matches the actual bytes against a big database of known signatures. If the bytes at this offset look like this, it is a PDF. Like that, it is a JPEG. And so on, for thousands of formats. Now, the Office suite generates the print job as PostScript, and near the very top of that PostScript it stamps the date the file was created. On a Tuesday, that date string begins with the letters T, T-U-E. And buried in that signature database was an entry for an obscure old format, an Erlang JAM file, whose signature was an entire literal date, Tuesday, the 22nd of January, 1991. Whoever added that entry did not escape the spaces. In that file format, an unescaped space ends the pattern. So instead of matching that whole long date, the rule collapsed down to matching the three letters T, U, E, at one specific position near the start of the file. Which is exactly where the Office suite writes its date. So the chain is this. It is Tuesday. The document header begins with T, U, E. The file type detector confidently announces that this PostScript document is an Erlang JAM file. The print system looks at that and says, quite reasonably, I have no idea how to print an Erlang JAM file. And the job dies. On Wednesday the header says W, E, D, nothing matches, and everything works perfectly. 2 lessons from this one. First, when something breaks, map the whole path, not just the part you wrote. There was an entire type detection step between the user and the printer that nobody had in their mental model, and that is where the bug lived. Second, and this one costs the industry a fortune, configuration is code. That signature database was not a program, it was a data file, so nobody reviewed it or tested it the way they would test a function. One missing / character in a data file shipped a defect to millions of machines. Your YAML, your regular expressions, your environment variables, your infrastructure definitions. All of it is code. Review it like code. Second question, and this one is uncomfortable on purpose. Think about the project you are working on right now. Between the moment a user clicks something and the moment they see a result, name one component in that path whose source code you have never read. A library, a driver, a proxy, a framework internal. Pause and name it. Statistically, that is where your next really painful bug is going to come from. Tell me in the comments what you picked. Case 4. We are leaving software entirely now, and this is the one that changes how people think about what a computer even is. December 2008, at Sun Microsystems. An engineer called Brendan Gregg is demonstrating a new set of tools for monitoring storage performance in real time. Live latency, drawn on a screen, as it happens. And to make a point, he walks over to a rack packed with spinning hard drives, leans in, and shouts at them. And on the screen behind him, the latency graph jumps. Immediately. In the same second. It is not a trick and it is not a coincidence, because he does it again, and it happens again. His colleague filmed it, the clip went everywhere, and it is still passed around today, because watching a man make a storage array slow down by yelling at it rearranges something in your head. The physics is straightforward once you say it out loud. Inside a mechanical hard drive, the read head is not touching the disk. It is flying above it, at a height measured in nanometers, over a surface spinning at thousands of revolutions per minute. The tolerances are absurd. And sound is not an abstraction. Sound is a pressure wave. Pressure waves move things. Shout at the enclosure vibrates, the vibration reaches the head wanders fractionally off the track it was reading, and the drive has to wait for the platter to come round again and try once more. That retry is the spike on the graph. And before you file this under fun trivia, it is a genuine operational hazard. Data centers have taken real outages from exactly this mechanism. Inert gas fire suppression systems, when they discharge, are extremely loud, and there are documented incidents of that noise knocking storage arrays offline. Alarms, building work, and poorly mounted cooling fans all do smaller versions of the same thing continuously. The lesson is one that programmers resist, because we like to think we work in a clean, logical world of ones and zeros. We do not. Every abstraction you use is being held up by a physical object that has a temperature, a resonant frequency, a power supply, and an environment. Most of the time the abstraction holds and you never think about it. When it leaks in ways that look like magic, and you will never find the cause in the code, because it is not in the code. And case 5, the best one, because it took 17 years to solve and the answer was about 30 meters away the entire time. Parkes Observatory in New South Wales, Australia. A 64-meter radio telescope and a genuinely famous instrument. Since the late 1990s, Parkes had been recording strange, short bursts of radio energy. They were named peritons, after a mythical creature which tells you how much anyone understood about them. And these were not a harmless curiosity, because at the same time astronomers were detecting fast radio bursts. Those are real, genuinely cosmic, immensely powerful events from billions of light years away, and they are one of the most exciting discoveries in modern astronomy. The problem was that the unexplained signals looked uncomfortably similar to the real ones. So there was a serious question hanging over the whole field. Were the great discoveries real, or was the telescope generating its own ghosts? The clues were there for years, and in hindsight they are damning. The bursts arrived during office hours. They clustered around the middle of the day. They showed up across the whole dish rather than from one point on the sky, which is a strong hint that whatever this is, it is not in space. It is here. The break came in January 2015, when the observatory had a receiver running specifically to monitor local interference. 3 new bursts arrived, and this time the team could see that each one came with a companion signal at 2.4 GHz. And 2.4 GHz is a very, very familiar number. It is the band used by wireless networking, by Bluetooth, and by one appliance in particular. It was the microwave ovens in the observatory kitchen. Specifically, and this is the detail that makes the story, it was not microwaves running normally. It was staff opening the door before the timer had finished. Interrupting the cycle that way shuts the magnetron down abruptly, and that abrupt shutdown radiates a burst of energy that a telescope built to hear the faintest whisper in the universe picks up without any difficulty at all. 17 years of an unexplained astronomical phenomenon, and the cause was hungry astronomers who could not wait the last for seconds. And I want to be clear that this is not an embarrassing story. It is a triumphant one. The team did not quietly discard the awkward data, and they did not hand-wave it away. They instrumented their own environment, found the correlation, and then went and reproduced the signal deliberately, with a microwave oven, on demand. That is the whole game. Once you can produce a phenomenon on command, you own it. And the real value is what happened next. With the false signals explained and eliminated, the genuine fast radio burst detections became far more trustworthy. Cleaning up your instrument is what makes your results mean something. The lesson generalizes far beyond astronomy. Before you conclude that your measurement is showing you something extraordinary, rule out the possibility that your measuring equipment is producing it. And in software you have instruments everywhere. Your logging. Your metrics pipeline. Your benchmark harness. Your profiler. If you have ever benchmarked something and found that adding a log line made the code faster, you have met your own periton. The observer was changing the observation. Third question. Of the 5 cases, which one do you think was genuinely the hardest to find, and why? My answer is the Tuesday bug, and here is my reasoning. Every other case left a fingerprint that pointed somewhere. 500 miles is a distance, and distance implies physics. 4096 is a power of 2, and a power of 2 implies binary. The shouting was reproducible on demand. The telescope bursts correlated with the clock. But Tuesday? Tuesday points nowhere. There is no physical mechanism by which a day of the week can reach a printer. You have to already suspect string matching to even start looking in the right place. Tell me if you disagree, because I think this one is arguable. So let's pull the thread that runs through all 5. In every single case, somebody reported something that sounded absurd, and the default institutional response was to assume the reporter was confused. The professor with the 500-mile email. The office that could not print on Tuesdays. The astronomers with signals that turned out to be lunch. And in every single case, the report was an accurate, faithful, honest description of what was actually happening. The reporters were never wrong about the observation. They were only ever wrong about the explanation, and explaining it was never their job. Which gives us a method, and it is the thing I actually want you to take away. 1. Believe a symptom, and distrust only the proposed cause. 2. Ask what changed, because something did. 3. Look for a fingerprint in the numbers. A power of 2 means binary. A distance means physics. A time of day means humans. 4. Map the entire path, including every component you did not write and have never read. 5. Get to the point where you can reproduce the fault on demand, because until then you are guessing, and after that you are finished. And one last uncomfortable thought. The phrase "it works on my machine" is treated as a joke or an excuse. It is neither. It is a clue, and quite a strong one. It means there is a real, findable difference between two environments, and you have not identified it yet. Every case in this video was, at bottom, exactly that. Something worked here and not there, and the difference was a config file, a cosmic ray, a calendar, a sound wave, and a microwave oven. So which of the 5 got you? Which one did you not see coming? Tell me in the comments, and if you have your own impossible bug, the kind nobody believed until you proved it, I genuinely want to read it, because those stories are how this profession actually passes knowledge down. If you enjoyed this, subscribe, because this is the first in a series of long-form deep dives, and the next one is about a problem nobody has solved at all. There is a $1 million prize sitting on it. It has been open since 1971, and if anyone ever cracks it, a great deal of the internet stops working. Thanks for watching.